Welcome to EMR Physics. I am Raju, NCERT 12th Physics. We are going to solve the numerical problems given in Chapter 8, Electromagnetic Waves. In this video, we are going to see how to solve the numerical problem 8.1. Let us see what are the data given in this problem. A capacitor is shown in a figure. This capacitor is made of two circular plates. Radius is given. Radius of the circular plates is given as 12 cm. The distance separation between the two plates is given as 5 cm. The capacitor is charged by an external source. The charging current is 0.15 ampere. What is asked? We have to calculate the capacitance and the rate of change of potential difference. Next, we have to find the displacement current. Lastly, we have to answer this question, that is Kirchhoff's first rule is valid at each plate? We have to explain our answer also. Now let us see how to answer this problem. First let us write what are the data given in this problem. Given radius of the circular plate is given. Let us take the radius as r. R is equal to 12 cm. We have to convert this centimeter to meter. Therefore, this is equal to 12 into 10 to the power minus 2 meter. Next, distance separation is given. D is equal to 5 cm. Again, converting this to meter, we will get this is equal to 5 into 10 to the power minus 2 meter. This is the radius of the circular plate of the capacitor. This is the distance separation between the two circular plates. Next, charging current is given, that is nothing but the conduction current. So I suffix C is a conduction current. It is given as 0.15 ampere. So this is a conduction current. First, what is asked? We have to find the capacitance. The two circular plates are parallel to each other. Therefore, we can consider this capacitor as a parallel plate capacitor. The capacitance of a parallel plate capacitor is given by C is equal to epsilon 0 A divided by D. Here epsilon 0 is the permittivity of free space. Epsilon 0 is equal to 8.85 into 10 to the power minus 12 Coulomb square, Newton to the power minus 1, meter to the power minus 2. A is the area of each plate. Area can be written as A is equal to pi r square. Since the plates are circular plates, this is equal to, we can take the pi as 3.14. R is 12 into 10 to the power minus 2. Therefore, r square is 12 into 10 to the power minus 2 whole square. Unit of area is meter square. We know the value of D. D is equal to 5 into 10 to the power minus 2 meter. So we know all these values. Therefore, we can easily find the value of the capacitance of the capacitor. So C is equal to, let us substitute the values, 8.85 into 10 to the power minus 12 into 3.14 into 12 into 10 to the power minus 2 whole square divided by 5 into 10 to the power minus 2. So if we do the calculation, we can find that this is equal to 8.00 into 10 to the power minus 12. This is the capacitance of the capacitor. Unit of capacitance is farad. Now we can write the 10 to the power minus 12 as pico. Therefore, this is equal to 8.00 picofarad. 1 pico is equal to 10 to the power minus 12. This is the answer for the first question. Next, we have to find the rate of change of potential difference. Second, we have to find rate of change of potential difference. The rate of change of potential difference is dV by dt. We have to find dV by dt. The charge on the capacitor is given by Q is equal to C into V. Q is the charge, C is the capacitance, V is the potential difference. Differentiating this with respect to time, we will get dq by dt is equal to C into dV by dt. Here C is constant. We have to find the value of dV by dt. dV by dt is equal to C will come to the denominator. So dq by dt divided by C. dq by dt is the rate of flow of charge. The rate of flow of charge is defined as current. So this is equal to I divided by C. Here this I is the charging current. Charging current is given as 0.15 ampere. Value of C is, already we have determined this value, 8 picofarad. The picofarad is converted to farad. So 8 into 10 to the power minus 12. If we do the calculation, we can find that this is equal to 1.875 into 10 to the power 10. This is the dV by dt. That is, the rate of change of potential difference is equal to 1.875 into 10 to the power 10, and the unit is volt per second. Unit of potential difference is volt. Unit of time is second. Since the time is in the denominator, the unit is second to the power minus 1. So this is the answer for the second question. Next, let us find the displacement current. Now let us calculate the displacement current. Displacement current is taken as I suffix d is equal to what? The electric field inside the capacitor can be written as E is equal to sigma by epsilon 0. Here this sigma is the surface charge density. Sigma is equal to charge by area, which is known as surface charge density. Therefore E is equal to Q divided by A divided by epsilon 0, which can be written as E is equal to Q divided by A epsilon 0. The electric flux can be written as phi suffix E is equal to E into A. E dot A is equal to EA cos theta. Here theta is equal to 0. Therefore cos theta is equal to 1. Therefore we can write the electric flux is equal to EA. Now using this relation we can write phi suffix E is equal to Q divided by A epsilon 0, and this A is into A. We can cancel A. Therefore this is equal to Q divided by epsilon 0. If we cross multiply, we will get epsilon 0 phi suffix E is equal to Q. Differentiating on both sides with respect to time, we will get epsilon 0 d phi suffix E by dt is equal to dq by dt. This term is nothing but the displacement current. On the right hand side, we are having dq by dt. We know that dq by dt is the rate of flow of charge. Rate of flow of charge is the charging current. That is, dq by dt is nothing but the charging current or the conduction current. This is equal to I suffix C. So the displacement current is equal to the charging current. Hence this is equal to, what is the charging current? The charging current is 0.15 ampere. It is given in this problem. Therefore the displacement current is equal to 0.15 ampere. So this is a displacement current. Now let us answer the next question. The third question is Kirchhoff's first rule is valid at each plate? Explain. Let us consider this is the first plate and this is the second plate. I suffix C is the conduction current. I suffix D is the displacement current. Outside the capacitor, the displacement current is equal to 0. Inside the capacitor, the conduction current is equal to 0. The current entering at the first plate is equal to I suffix C. This is the current entering into the first plate. Current leaving from the first plate is equal to I suffix D. So this is the current entering and this is the current leaving. We have already seen that displacement current is equal to conduction current. That is, the current entering towards the first plate is equal to current leaving from that plate. So current entering is equal to current leaving. This is a Kirchhoff's first rule. Hence, the Kirchhoff's first rule is valid at the first plate. Similarly, we can prove that Kirchhoff's second rule is valid at the second plate. So this is the answer for the third question. If you find this video is useful, please subscribe the channel, share it to your friends. If you have any doubts, comment below. Thank you for watching this video.